this module, I want to move on to the high temperature realm with seawater in the subsurface attaining temperatures in excess of 350, 400 degrees and pressures in excess of 30 megapascals. Because in that situation, the state of seawater changes into what's known as the supercritical state, where the seawater, which can contain as much as 48% NaCl, dissociates into two phases, what is a freshwater vapor and a cloud of ultrafine crystals of both sodium sulphate and sodium chloride. Many have argued that this association of a supercritically formed salt can explain some of the high salinities we see in major rift basins such as the Red Sea and the Dalal. Let's have a look at this process of how we create supercritical seawater and the possibility of significant volumes of halite and sodium sulphate in fractures in the hot subsurface beneath the world's oceanic crust. We'll look at whether we think it can explain large volumes of the halite that occurs in rifts and collision belts, these megahalite and megasulphate associations. But before we do that, let's go back and do a little bit of Chemistry 101 and remind ourselves of the difference between prograde and retrograde salts. A prograde salt has a solubility that increases with temperature. So we're looking at how much of a salt we can put into solution as the temperature increases, typically measured in weight % of the particular salt phase. Here I plotted up what are two prograde salts. With prograde salts, we see increasing solubility with increasing temperature. The reactions move to the right, where we put solid components into solution, into ionic solution as ionic species as we increase the temperature. This is what controls the solubility of salts, which are endothermic, where the average kinetic energy of the molecules in that brine is increasing. The Brownian motion is increasing with temperature. And so with an endothermic reaction, that increase in kinetic energy in a prograde salt allows the solvent molecules, in this case the polar water molecules, to more effectively break down the solute molecules. And so we see solubility increasing as the temperature increases. In a sodium chloride solution with an increasing temperature, before we hit the critical point and pass into the supercritical phase, so around 400 degrees centigrade, that brine can contain as much as 48% halite. Prograde salts are endothermic, whereby the Brownian motion dominates and we increase the ability of that salt to go into solution at higher temperatures. Contrast that with a retrograde salt. Remember, we talked about anhydrite as a retrograde salt when we looked at the hydrothermal forms of anhydrite on the deep sea floor a few chapters ago. A retrograde salt is described by any solution process where we have a decrease in solubility with an increase in temperature. Now, in any solution process where the solute and the solvent, in this case seawater or water, are in dynamic equilibrium with the solution, if we can introduce heat, we'll disturb that equilibrium. This is the Le Chatelier principle, where we see that the disturbed equilibrium is counterbalanced by a shift in the position of the equilibrium. In contrast to an endothermic reaction that we see in prograde salts, with retrograde salts, we see exothermic reactions. We're giving out heat as the reaction takes place. That additional heat shifts the equilibrium position to the left. So for calcium sulphate going into solution, we're moving that equation to the left, whereas with the prograde salts, with increasing temperature, we were moving it to the right. That increased availability of exothermic heat shifts that equation to the left, to counterbalance that disturbance created by the introduction of heat to the equation. That shift in equilibrium is a key feature of all retrograde salts. As a consequence of that shift to the left, the dissolution process slows down, so we have more undissolved solute in increasingly hotter waters, and so the solute showing a retrograde solubility with respect to increasing temperature. That's the contrast between a prograde and a retrograde salt. Endothermic versus exothermic. Now let's move into the state of supercritical seawater and see what happens as we increase the temperatures above around 374 degrees centigrade. What is supercritical water and how does it occur? As the temperature and pressure of liquid water is raised, once we reach the critical point, we pass into a system where we move beyond the critical point, which is around 374 degrees centigrade and around 22 megapascals, In that liquid vapor space, where previously we had a situation of either solid vapor or liquid vapor, as we move into the supercritical phase, indicated by the red dot CP, as we move into the supercritical phase, we get small but liquid-like hydrogen bond clusters dispersing into what is a gas-like environment. Those conditions of temperature and pressure must exist in much of the crust and mantle. Much of the water phase that we see in the deep subsurface is supercritical. What distinguishes supercritical water is that it becomes a very poor solvent for electrolytes, for the sodium and the chlorine and so on, which in lower temperature pressure states tend to form clusters as ions go into solution, surrounded by polar water molecules. But once we hit the supercritical state, we find that due to its relatively low permittivity and the breakdown of hydrogen bonding in the water molecules, we get a mass salting out of the previous ionic components that were in solution. So we get what is known as salting out, where we get very fine-grained particles of halite and sodium sulphate coming out of solution in that supercritical phase. The supercritical phase is also, because it's got poor hydrogen bonding now, we've broken down the hydrogen bonds in that phase, it becomes an excellent solvent for non-polar molecules, many of which become entirely miscible. It's one of the ways we form decaffeinated coffee. Supercritical water has no surface tension with its gas, liquid, and other supercritical phases. There's no such interfaces in existence in the supercritical phase. In contrast to liquid water, hydrogen bonds in supercritical water have only broad, weak interactions. They're not dynamically rigid or structurally stabilizing, even when they're at typical liquid-like densities of around 1,000 kilograms per cubic meter, or 1 gram per cc. Once we obtain that supercritical state, we find that the water molecules are no longer held by the hydrogen bonds, and so they can float about as free radicals. We can think of supercritical water as a liquid-like gas. And this is why supercritical water has such high solubility for non-polar reactants, because of its inherently high reactivity. Now, supercritical water tends to be acidic and non-polar, whereas liquid water, because of its hydrogen bonds, tends to be polar and neutral. Once we obtain that supercritical phase, previously dissolved components, which in seawater is dominated by sodium and chlorine and also by sodium and sulphate, those previously dissolved components precipitate out in a process known as shock crystallization, where they form these ultrafine particles of salt in our supercritical phase. A seawater brine, as it evolves, has two critical points. It attains its first one at around 405 degrees centigrade under pressures of about 30 megapascals, which is equivalent to a water depth on the seafloor of about 2.8 kilometers in terms of pressure. But of course, we have to have a heat source to bring our temperatures up to such high levels. Once we go above 405 degrees, the seawater becomes supercritical, and then we have two phases, gas and liquid, coexisting, and we have a massive salting out or crystallization of ultrafine salt particles. If we then cool that supercritical fluid to temperatures below its critical point, we find that it can redissolve those solid salts. If, on the other hand, we continue to heat, we find a second critical transition, which is called the upper solidus line. So above a temperature of around 720 degrees centigrade, the supercritical changes its state, once again its phase state, and changes partly to brine, which can then redissolve the salt. So there is a Goldilocks field between around 375, 400 degrees and 700 degrees, where we can have mass crystallization of the phases, the ionic species, which were in solution. To summarize, under sufficient confining pressure and heating to supercritical temperatures with the appropriate pressures, temperatures between around 400 and 720 degrees centigrade, the brine flashes into a mixture of water vapor and a range of ultrafine microscopic salt particles made up of sodium chloride and sodium sulphate crystallites. So we can think of it as, if you like, a solubility process for halite and also for sodium sulphate, in terms of in the brine until temperatures up around 400 degrees, and then out of the brine if the temperature increases beyond 720 degrees, or if the brine cools, those ultrafine crystals will go back into solution. We can think of this process of supercritical salting out as an in and out and in process that's likely to oscillate a number of times. As we increase the temperature beyond our 374 degrees centigrade or our 675 degrees Kelvin, the structure of the solution decays. And so that polar attraction, which moves those solid ionic species into solution, that electrostatic attraction coming off the polar water molecules, breaks down as we are destroying the effectiveness of the hydrogen bond network. Crystallization, the salting out, defines the point where that hydrogen bond network is deteriorated to such a degree that it's no longer able to shield those salt ions from each other. And so we get a recombination, form those flashpoint crystals. Those salts are no longer soluble in the water, which is now in a vapor-like state where all three phases coexist. If we move into temperatures which are even higher, beyond about 950 to 1000 degrees Kelvin or 720, 750 degrees centigrade, the regime emerges where once again those ions become soluble, once again as electroneutral ion pairs surrounded by water molecules. So this is a Goldilocks field where conditions are ideal for the flashpoint. A number of workers, mostly by Hoagland and others and his co-workers over the past 2 decades, have argued that this supercritical phase salting out explains some of the large volumes we see in hot rifting associations. So they use it to explain some of the massive evaporite deposits, as in the Delol Depression and on the deep sea floor of the Red Sea. It's certainly a process that happens throughout the hotter portions of the crust where we have deeply circulating seawater. But this is not evaporite. It's not a solar-driven evaporation process. This is a hydrothermal process related to elevated temperatures and pressures in the subsurface. And so these salts that occur as flashpoint salts in the supercritical realm are going to have a number of distinctive properties. If we look at the outsalting and the shock crystallization associated with supercritical seawater, in terms of the internal fabrics, we see these ultra-fine crystallize, 10 to 100 microns across, and they're microscopically mixed chemistries and minerals dominated by the major components in seawater, namely the sodium chloride and the sodium sulphate salts. They have mixed chemistries. At the microscale, within the fractures, they will be intergranular, displacive cements. Any lamination that may build up on the margins of these fractures or in the pores will be irregular, and it will be discordant to any bounding beds in the hosting volcanogenic sequence. At the macroscopic scale, they'll tend to occur within intrusive pipes, fractures, dikes, towers, and lenses. They will have stable isotope signatures and brine inclusions that indicate high temperatures of formation in excess of 300 to 350 degrees, and they'll be dominated by the dominant salts in seawater, namely halite, sodium sulphate, and anhydrite. Depositionally or precipitationally, they'll form under elevated conditions of temperature and pressure in fractures. It's argued that massive salts could accumulate on the deep sea floor from this process, but nowhere in the world has this process of hydrothermal salts accumulating on the seafloor via elevated salting out point crystallization at the supercritical field been observed. What has been observed is, as we discussed 2 chapters ago, widespread hydrothermal anhydrite due to its retrograde solubility and the fact that as we heat seawater, the solubility of calcium sulphate decreases and we form those very widespread but ephemeral calcium sulphate and hydrothermal salts that we discussed 2 chapters ago. In terms of what's going to be associated with this precipitational sequence for supercritical halite and the other associated flashpoint salts, we'll be looking at what are igneous intrusive and contact metamorphic halos, where we'll see halite coats on what are hydrothermal basaltic breccia clasts and fractures. Now let's contrast that with the evidence we see for solar-driven evaporation, where solar heating with predominantly prograde precipitation creates very widespread and thick evaporite beds, which typically are mono or biomineralic because of the need for holomixis, and quite often they preserve remnants of the primary textures. The chevrons are the other textures that we see in many portions of these thick salt deposits which have not flowed. Once they're flowed, we'll see this biaxial overprint that we discussed in the salt tectonics course. So we'll tend to see beds at the macro scale, along with loaded diapuric structures, plugs, walls, anticlines, and so on. The stable isotopes that we see in typical evaporite deposits have stable isotopes and brine inclusion signatures that indicate precipitational conditions which are quite low, with temperatures of less than 100 to 200 degrees. And we'll see a characteristic evaporation series, not a flashpoint with mixed mineralities, but an evaporation sequence, a sequential evaporation going from gypsum and hydrite through halite into the magnesium sulphate enriched brines, as we see in modern seawater, or more magnesium sulphate depleted brines with the calcium chloride oceans in large portions of the Phanerozoic ocean chemistry. Depositionally, we'll see low temperature and pressure at deposition with the superposition, the stacking of beds showing sequential, gravitationally controlled texturing, followed by, with loading, quite early sometimes, halokinesis. We'll tend to see climatic associations with saline arid zone carbonates and siliciplastic halos, which preserve many sedimentary features associated with that succession. So these are the characteristics we should see if we compare the hydrothermal halites, the critical point supercritical halites, with typical evaporite textures. In my mind, we don't see this process creating large volumes of depositionally textured halite, which is driven primarily by solar heating. We don't see a lot of halite in fractures. Very little hydrothermal halites actually been documented where we've drilled hot portions of the crust. However, we do see on parts of the seafloor the escape of supercritical, deeply circulated seawater. And in 2006, in the Comfortless Cove Turtle Pit area at around 5 degrees south and 13 degrees west in the Atlantic Ocean, northeast of the Ascension Isles, we see fluids creating typical black smoker chimneys. But what was interesting in the region of the Comfortless Cove and the Turtle Pit was that in the early 2000s, a couple of these mounds were capped by chimneys that were emitting gas bubbles. And the temperatures measured in those gas bubbles they were emitting showed that this was a supercritical phase seawater. In other words, at a bottom depth of around 3,000 meters in this area, these fluids were venting at temperature pressure conditions around and above the critical point of seawater. So if we plot up now the measured temperatures around a range of hydrothermal vents in mid-oceanic ridges around the world, we can see that most follow that typical sub-supercritical temperature line. And I've plotted in a number of the various documented temperatures and pressures and water depths for a range of hydrothermal vents. Notice how the Turtle Pits and the Comfortless Cove sit out beyond the critical point in what is the edge of the supercritical association. When temperatures were being measured, there was a short burst, around 20 seconds of venting of these bubbles where the temperatures measured were 460 degrees centigrade at a depth in the ocean of 3,000 meters. So these are clearly at temperatures and pressures above critical point. And as you can see from those red circles, these are some of the hottest fluids observed in venting smokers. The sampling of those fluids showed that they were enriched in iron, copper, cobalt, and molybdenum, which once again is reflective of that extremely high temperature and the importance, therefore, of the phase separation and the chloride complexes in the metal transporters in the fluids issuing. These are typical VHMS-type temperature pressure associations on the deep ocean floor. What's interesting is if we look at these vents and ask the questions, what's there in terms of the ionic salt phases? Anhydrite, as a hydrothermal precipitate related to its retrograde properties, is commonplace around the black smokers where the metal sulfides are commonplace, along with some anhydrite. So anhydrite, calcium sulphate, is commonplace in both the vent chimneys and their associated longer-term breccias. But there was no halite documented from these supercritical fluids. The anhydrite is the typical hydrothermal anhydrite association. It's ephemeral. As we cool things down, that anhydrite is going to go back into solution. And this is a major problem with this association to form these supercritical deposits. We need to pond the brines. And so we're not going to see halite. We're not going to see, if it does exist as a supercritical phase, we're not going to see halite as hydrothermal halite on the open ocean floor. We may see it on the seafloor, but of course the problem is if we look at areas where people have extrapolated this happening in the Red Sea, around the Atlantis Too Deep, for example, or around the Dalal Mound, as we've discussed in other courses, these textures that we see in these deposits across here before they move into halokinesis are depositional solar evaporite textures. We don't see ultrafine mixed phase salts. So these vent sites, wherever we see them, even in the hydrothermal vents at Dalal Mound, which we've talked about, and you can read about it in my 2016 book or that Bastow paper in 2013, those vent sites, although there must be supercritical conditions below, are not producing long-term salt accumulations. I don't say this process isn't creating ionic components. There'll be varying volumes of salting out in various hydrothermal systems that very likely exert a long-term effect on the relative supply and the ionic proportions and salinity in seawater. For example, we talked about in the oceanic Phanerozoic chemistry, sylvite versus carnallite as magnesium sulphate versus calcium chloride oceans that were tied to varying rates of seafloor spreading. That was pointed out as long ago as the mid-90s by Hardy. Is this a testable hypothesis, this notion of hydrothermal halite supplying large volumes of sodium chloride into what are classically interpreted as evaporite accumulating areas, such as the floor of the Red Sea or in the Dalol Mound? Well, I think not. And I think we need to draw a distinction between a hydrothermal salt and a salt formed via solar evaporation, an evaporite salt. Most evaporite textures transition from arid primary solar evaporation textures into halokinesis throughout the rock record. They may not all go to halokinesis. We may retain bedded textures where we see the preservation of abundant depositional and early diagenetic textures. Nowhere in the world do we have documented examples of salting out halite mixtures anywhere in the world. Or do we see the massive textures that should be associated with those seafloor fractures on the seafloor, nor do we see them in the serpentinites. We see in the serpentinite deposits on the seafloor, as we saw in the previous chapter, significant volumes of the carbonates. How do we prevent dissolution of any salted out seafloor products, hydrothermally formed, once that magmatic or metamorphic heat source dissipates? The ocean is a huge near-isochemical blanket, relatively cold, undersaturated with respect to salts, covering the world's seafloor. Even in the classic VHMS deposits, where we know hydrothermal anhydrite made up 50 or 60% of the total volume during the process of formation of those hydrothermal structures and acted as a sulfide source, that anhydrite has long gone. If we step back and say, well, can this be a significant testable hypothesis? Well, certainly the criteria blur for the hybrid salts that were created by supercritical salting at depth in fractures, in vugs, not as depositional systems on the floor of the ocean. That system could be supplying ionic species into venting systems, which are modifying the chemistry of seawater as they dissolve from the fractures, as we cool the system down, and they migrate to the Earth's surface as saline waters. So we may have a source of saline waters, hydrothermal saline waters, that can then precipitate via sump restriction and solar evaporation. And of course, the types of salts we're going to see will be related to prograde versus retrograde responses. Bed preservation of any massive halite deposit requires sufficient time and burial to allow thick associations of halite and or anhydrite and or gypsum to accumulate. So any exposure to cooler conditions and associated with long-term exposure to seawater is going to be problematic in preserving those structures. If we go around the world and look at the deep marine seafloor, even in the floor of the Red Sea, away from the halokinetically seepage features on the brine sumps on the floor of the Dead Sea, deep marine seafloor is sediment starved. And so there's no isolating blanket or carapace to any salt that's accumulating there. We have to have density stratification on the seafloor associated with the dissolution of a pre-existing halite mass. So to me, there's certainly the possibility of hydrothermal salts, but they are not evaporites, and they are not volumetrically significant in all of the massive salt deposits we see around the world. We know the difference between a testable and a non-testable hypothesis for this type of association. In the next chapter, we're going to look at the fourth and final association of hydrothermal salts, where we'll look at hydrothermal and mixing zone phreatic gypsums forming as cavern fills related to juvenile waters and or mixing of hot calcium sulfate saturated water with cooler phreatic waters.